The year 1932 witnessed the unfolding of a profound revelation, a cornerstone in the edifice of quantum mechanics. This achievement, attributable to Wolfgang Pauli, elegantly wove together two seemingly disparate properties of fundamental particles, their spin and their statistical behavior. Pauli's contribution, a feat of mathematical rigor and conceptual clarity, irrevocably altered our comprehension of matter and its interactions. The resulting principle, a testament to the elegant architecture of the universe, remains a linchpin in our understanding of the physical world. Before Pauli's seminal work, the theoretical landscape concerning the quantum nature of particles was complex and fragmented. The wave-particle duality, established by the likes of de Broglie, had begun to challenge classical physics. The concept of spin, an intrinsic form of angular momentum, was emerging initially through the study of atomic spectra. This intrinsic property, unlike classical angular momentum, possessed quantized values and, crucially, could take on half-integer values too. The challenge lay in reconciling spin with the statistical mechanics that described the behavior of large ensembles of particles. Two primary statistical descriptions existed: Bose-Einstein statistics, applicable to particles, that favoured occupying the same quantum state, and Fermi-Dirac statistics, applying to those that obeyed the Pauli exclusion principle, barring any two identical fermions from occupying the same quantum state simultaneously. The link between spin and statistical behavior had yet to be rigorously formulated. The existing framework in quantum mechanics, while successful in describing various phenomena, offered no clear, underlying principle that connected spin and statistics. This disconnect posed a fundamental problem. Pauli's work, born of these challenges, provided the unifying link. He arrived at a groundbreaking conclusion that dictated the behavior of all particles that are currently known. He established a rigorous mathematical proof demonstrating that particles with half-integer spin, the fermions, necessarily obeyed Fermi-Dirac statistics. Conversely, particles with integer spin, the bosons, were compelled to follow Bose-Einstein statistics. This connection was not merely an observation, it was a mathematically derived consequence of the underlying quantum mechanical principles, specifically those related to relativistic quantum field theory. The core of the argument lay in the requirement for relativistic invariance, which essentially means that the laws of physics should remain the same regardless of the observer's motion. Pauli meticulously constructed the proof, relying on the principles of quantum field theory. With its elegant formalism, he utilized the concept of field quantization, which posits that particles are merely excitations of underlying quantum fields, and the principles of symmetry and antisymmetry to build his argument. He investigated the properties of particle creation and annihilation operators, carefully considering their commutation relations. The use of operator formalism allowed Pauli to extend his argument to multiparticle systems. The mathematical intricacy and conceptual depth of the proof were considerable, demanding a high degree of mathematical sophistication. The immediate impact of Pauli's discovery was profound. It provided a theoretical justification for the observed behavior of electrons, protons, and neutrons, all of which possess a spin of 1/2 and are therefore fermions. The exclusion principle, which had previously been posited as an empirical observation, now found its rigorous foundation. It explained the stability of atoms, preventing electrons from all collapsing into the same lowest energy state. The atomic structure of the elements and the structure of matter became at once better understood. Also, as a consequence, the statistical behavior of photons, which have a spin of 1 and are bosons, could now be fully understood, providing a more complete view of light. The Pauli principle provided a framework for understanding the nature of chemical bonding and molecular structure. The impact rippled through other fields of physics. The understanding of the behavior of electrons in metals, for example, was refined and deepened, impacting the physics of solids. The principle became foundational for the development of nuclear physics. The observed behavior of atomic nuclei and the behavior of the different types of nuclear particles fit into the framework of Pauli's principle. The implications extended beyond the realm of physics, offering insights that informed the broader scientific community. The legacy of Pauli's work is far-reaching and enduring. His connection between spin and statistics continues to shape our understanding of the fundamental building blocks of the universe. Modern quantum field theory, the language in which we describe all known fundamental interactions, is built on the principles that Pauli helped to establish. The standard model of particle physics, which classifies fundamental particles, relies on his classification of bosons and fermions. Superconductivity, a phenomenon in which certain materials exhibit zero electrical resistance at extremely low temperatures, is fundamentally dependent on the pairing of electrons, which are fermions, into Cooper pairs, with a combined spin of 0, acting as bosons. The concept continues to inform the creation of new technologies, the continued investigation of topological insulators, materials that behave as insulators on the inside but conduct on the surface, relies on this insight. The principle has found applications in areas such as condensed matter physics, quantum computing and cosmology. From the intricate dance of particles within atoms to the large-scale structure of the universe, Pauli's principle continues to be essential. A principle has become a pillar of theoretical physics. Pauli's principle and its derivations have undergone scrutiny and refinement over time. The initial formulation, elegant as it was refined by the development of more sophisticated quantum field theories, incorporating ideas from relativity and particle physics. The discovery of the connection prompted other physicists to develop the principle further and seek its implications. The work of physicists like Oscar Klein and Pascual Jordan in formulating quantum field theory provided a solid foundation for Pauli's work. The contemporary reception of Pauli's work was overwhelmingly one of respect, even awe. Its mathematical rigor and conceptual elegance were immediately recognized by his peers. Though the intricacies of quantum mechanics made it initially daunting to grasp, its explanatory power, its ability to account for previously unexplained phenomena, secured its place in scientific discourse. The impact of the work was quickly recognized, and it became an integral part of the emerging quantum physics paradigm. The principle's enduring power has transcended early criticisms. It has withstood the test of time and has become a cornerstone in explaining the observed behavior of all known particles. Several factors contributed to Pauli's success in deducing the spin statistics theorem. His deep understanding of quantum mechanics, coupled with his rigorous mathematical ability, gave him a powerful toolset for unraveling the problem. His ability to synthesize different areas of theoretical physics, including quantum mechanics, relativistic invariance, and statistical mechanics, proved crucial. Pauli also benefited from the intellectual climate of the time. The vibrant scientific community of the 1920s and 1950s fostered a culture of collaboration and exchange of ideas. He was immersed in a community of brilliant minds. The contributions of Werner Heisenberg, Niels Bohr, and Paul Dirac, among many others, provided the tools and framework that Pauli then used to develop his theorem. Their collaborative efforts served as catalysts for scientific breakthroughs. Dirac's work in relativistic quantum mechanics, with its introduction of the Dirac equation, was particularly influential. Indeed, Dirac also arrived independently at this connection using a different method. Though Pauli's work came first, the theorem itself serves as a testament to the power of theoretical physics to illuminate the fundamental workings of the universe and stands as a symbol of intellectual brilliance. The influence of Pauli's work has been immense, extending across the many branches of physics. The impact on quantum field theory is undeniable. His connection provided the core of quantum computation. The principle has been instrumental in the development of the standard model of particle physics, allowing a classification of the fundamental particles based on their spin and statistics. The work also spurred further investigations into the nature of fundamental particles and their interactions. The theorem's continuing influence on physicists is evident. It has inspired generations of theorists to explore the intricacies of quantum mechanics and to seek a deeper comprehension of the universe. The principle provided a unifying framework and is still used today. In conclusion, Pauli's 1932 work on the connection between spin and statistics was a landmark achievement. It provided a definitive link between the intrinsic spin of a particle and how it behaves statistically. It provided a critical insight impacting several fields. Its impact continues to resonate throughout the world of physics. The spin statistics theorem stands as a beacon, illuminating the intricate dance of matter and energy and reminding us of the enduring power of human curiosity and the elegant language of mathematics in unlocking the mysteries of the universe.